All right, we're going to look at unit vectors right now. Unit vectors are special vector and defined to be such that it's a vector of or with a magnitude 1. So a unit vector just has a length of 1. There are a couple special unit vectors that we consider. So the first special unit vector has a length of 1 in the x direction. So imagine this vector here that has a length of 1 just in the x direction. And when it's just in the x direction and it's a unit vector, we give it the special, we call it a special vector, which is I. And because it's a unit vector and special, it's written with a little hat, and that's the symbol for the vector. Well, the I is a unit vector in the x direction. What do you think a unit vector in the y direction is? Following the alphabet, we call that the unit vector j. So j is a unit vector, length 1, that's entirely in the y direction. Lastly, a unit vector of length 1 in the z direction is called k. So vectors I, j, and k are each unit vectors, and they define our Cartesian coordinate system. So I is a unit vector in the x direction, j in the y, and k in the z. What we're able to do now is write a vector in terms of its components using I, j, and k. So let's suppose that we have some vector A, and its components are ax, ay, and az. Well, ax is the magnitude of the vector in the x direction, and ay is the magnitude of the vector in the y, and az is the magnitude of the vector in the z direction. So what we're able to do now is say vector A can be written as, well, the magnitude of the vector in the x direction multiplied by vector I. So that gives us, this is giving us both magnitude and direction. And multiplying it by I, since I is a unit vector and only has length of 1, the magnitude of this vector still is a sub x, but multiplying it by I does is it gives it the direction in the x direction. Okay, so then plus a sub y, which is the magnitude of the vector in the y direction, multiplied by its direction, not k, j. And lastly, we're going to add it to a sub z, which is the magnitude in the z direction, and then we need to give that the direction, so k hat. So there we have written vector A in component form using its respective magnitudes in the x, y, and z direction, and then we multiplied those magnitudes by I, j, and k to give it direction as well. Okay, well, one of the things that we're going to want to be able to do is take any vector and turn it into a unit vector. So let's imagine this vector here, which starts here and goes 3 over and then 4 up. So we're talking about the red vector right there. So how could I, first of all, how could I write that red vector using I, j, and k? Well, you know, if we define this to be we're defining this to be the x direction and this the y direction, then my red vector A is going to equal 3I plus 4j, because I went 3 in the x direction and 4 in the y direction. Well, how would I make it a unit vector? Right? How do I make that a unit vector? Well, the first thing that we need to do is find the magnitude of A. Well, the magnitude of A is just using the Pythagorean theorem. It's is 3 squared plus 4 squared, which is 5. So that's the magnitude of A. Is that a unit vector? No, it's too big. But all I need to do then to find a unit vector that's in the direction of A, so turning A into a unit vector. So in other words, I want to get something in the same direction of A, but only of length 1. All I need to do is find, a fifth of A to get rid of that 5. Or in other words, I'm going to take A and divide it by its own magnitude. And what I'm left with is a vector that's in the direction of A, but only has length 1. So if we do that, we would get 3/5 I plus 4/5 J. And this is an important skill for us to do mostly for next lesson when we start looking at multiplying vectors and dot and cross products. But for now, this is just a skill. The idea is how can we take a vector of any length and turn it into a unit vector? Okay, well, by writing vectors in their component forms, it allows us to add vectors really effectively. So let's first make a little diagram and then see where that goes as far as components. So let's imagine I've got a bug here, and there's some bug on the floor, and it goes over 1, up 1. So it's got this net walking distance of going over 1 and up 1. And then let's say it goes over 2, up 1. So now it's going to go from that point over 2 and up 1. Well, what we just did, we went over 1, up 1, over 2, up 1. What was my net change? Well, in the x direction, I went over 1, and then I went over 2. And in the y direction, I went up 1, and then I went up 1 once more. So 2. And so the idea of this really gets at the idea of adding vectors, where what we do is we can just add their components. So in other words, imagine if I had some vector A, which is AXI plus AYJ, and I wanted to add A to B, which is BXI plus BYJ. What we do is we just add their respective components. So our resultant vector, A plus B, is just going to be the sum AX plus BX in the I direction plus AY plus BY in the J direction. So if you can get vectors into their component form, it makes adding them numerically very straightforward. Okay, what else can we do with vectors? So now we can add them numerically, and I've actually I already did this earlier, multiplying a vector by a scalar. So let's imagine that I have some vector, let's call it a force vector, which is 2I plus 5J. So it's some force. What does that force look like? Well, just to kind of sketch it out, we've got 2 in the x, 5 in the y. So it's some vector that looks like that. What if we wanted to have a force that was 3 times as big? So we're multiplying a vector by a number, a scalar. So if I wanted a force 3 times as big, I want 3 times my force. Well, using substitution, that's just 3 times 2I plus 5J. And then we can just distribute that 3. So that's going to equal 6I plus 15J. So just as you would think, if you want to multiply a vector by a number, you just distribute that scalar across the respective components. Okay, so the last idea I want to touch on is an important idea in physics, which is called superposition. And the idea is this: when we talk about, usually when we're talking about the origin, here's where the origin is, or this is what the x direction, or this is the positive direction. What we're defining these things rather arbitrarily, uh, and it doesn't matter where you set the origin. So I could have the coordinate plane where it is now, or where this is the origin, or I could move the coordinate plane over here where this is the origin, and then we could essentially flip the coordinate plane too, where we could say, let's move it in this direction, and define the coordinate plane to look like that, or this, or anything of the sort. So um, what's critical, though, is that we just need to be consistent. So as soon as you start a problem, if I'm calling this y and that x and that z, and I'm calling this here the origin at the beginning of the problem, then that needs to be the coordinate system throughout the whole problem, or else we'll get into some sloppy trouble. Similarly, and we'll talk more about this in just a little bit, but we will be using right-handed Cartesian coordinates, which are set up as we see with the x going to the right, y going up, and z coming out of the page, and that's our we're going to consistently use that. But there also is the left-handed Cartesian coordinate plane, and you should be aware of that. But we for consistency's sake, we'll not be using that. So there we go. Just that's mostly math ideas. What we're looking at there is breaking vectors up into their components, looking at unit vectors, looking at I, J, and K as a way to describe a vector in its component form, and then thinking about how you can multiply vectors by a scalar.